I'm Gan Hui Kyung from Group 2. I'm going to present the control engineering assignment, which title is Convection Oven, with my teammate Tyrone Kang, Tong Jin, Gan Teki, and Lim Jin Hang. The convection oven is designed with a fan and exhaust system to ensure uniform heat distribution, allowing it to cook food faster than conventional ovens by reducing cooking time and operating approximately 20 degrees Celsius lower temperatures. The oven operates by circulating hot air within the chamber through the fan and exhaust system. It also incorporates an NTC thermistor to provide precise temperature control, ensuring consistent cooking performance. The objective of this study is to design a control system for regulating the temperature inside a convection oven, ensure a percent overshoot of less than 5%, and achieve a settling time of under 180 seconds. Secondly, to manually design a compensator that meets the specified performance criteria using CISO design tools. Thirdly, to analyze and compare the time responses of the uncompensated system, the manually uncompensated system, and the system compensated using CISO design tools. On this slide, I present the modeling of a convection oven. On the left, the physical model shows the main components, the heater powered by AC, the temperature sensors, and the control switch, the temperature control knob, and the door. Together, they form the oven's structure for heat transfer and regulation. On the right, the schematic diagram illustrates the control system. The desired temperature is set via the knob. The controller adjusts the energy input based on the feedback from the sensor, which monitor the oven's internal temperature. Disturbance such as heat absorbed by food, ambient temperature, and door opening are also factored in this system. Potentiometer controls the oven desired temperature using a temperature knob and biometric strip to regulate the heating element. It is connected in series with a 0.95 kilo ohm resistor across a 240 volt supply. The ovens operate between 100 and 250 degrees Celsius. The output voltage is 45.54 volt at 100 degrees Celsius and 151.2 volt at 250 degrees Celsius, showing a direct proportional between V out and temperature. The potentiometer sensitivity calculated as gradient of the trend line is 0.7044 volt per degree Celsius, reflecting the voltage change per degree Celsius. Now I'll explain the thermistor behavior and its transfer function. The output voltage is proportional to temperature given by V equal to Ct, where C is the potentiometer sensitivity. In the S domain, it becomes as shown in equation 1. The transfer function is ratio of output to input, as shown in equation 2, with C equal to 0.7044 volt per degree Celsius. This shows the linear relationship between temperature and voltage based on the thermistor sensitivity. Let's look at the heating chamber model. Heat is transferred to a mass until it reaches thermal equilibrium with the chamber. Following the law of conservation of energy as shown by equation 1, the rate of heat transfer is expressed as equation 2, which relates to the thermal resistance similar to Ohm's law equation 3. By combining these equations, we derive a dynamic heat equation that incorporates the time constant, giving us equation 4. Finally, the S domain, the transfer function is equation 5 for a time constant of 120 seconds. It simplifies to equation 6. The heating element consists of nickel wires encased in stainless steel tube, ensuring uniform heat distribution. Its dimensions are 0.0095 meters in diameter and 1 meter in length, giving it a volume of 7.126 times 10 power of negative 5 meter cube with a mass of 0.57 kg is designed for the efficient heat transfer. Considering the material's specific capacity of 490, using the electrical power equation 1 and the Laplace transformation, the transfer function for the system is equation 2. Operating at 850 watt and 110 volt, the current is calculated to be 8.936 ampere, demonstrating the heating element's efficiency in converting electrical energy into heat.
These are a reduction of work diagram for our system by multiplying the transfer function for heating element and heating chamber with a gain factor of 0.7044 for potentiometer. We will get the equation as shown in figure 3.5. And by using the formula shown at the right side, by summing into Hs equal to value of 1, we will get a third equation as shown in the right bottom corner, and dividing with the coefficient of f squared from the denominator side, we will get the equation shown in figure 3.6, which is the equivalent closed-loop transfer function. This is a Maillard calculation by coding side. For G1 is the equivalent transfer function of heating element and heating chamber, and G2 is after multiplying with the 0.7044, which is the gain factor for a potentiometer, and T1 is the transfer function for a feedback control system. Now we'll continue with the analysis part. For the first equation, it is a closed transfer function without compensator, and by comparing with the second equation, which is a general form for second order system, we will obtain the omega n and zeta. Then we can calculate the setting time, which is 960.03 seconds, and the percent overshoot is 40.69%. While for the stability, we will construct a rough table, and the first column is s power n, second column is coefficient of s power n, third column is coefficient of s power n minus 2. While for the coefficient of s power 0, we will calculate based on formula below, and you can notice that for the second column, there is no side change, so the system is stable.
For the stability of the system, the closed loop pool of the system are calculated using the equation 3 and theta is computed as equation 4. Then the pool zero diagram is plotted. Based on the pool zero diagram, all pools are lying on the left half plane only, therefore the closed loop system is stable. For the steady state error analysis, the open loop transfer function without compensator is shown as equation 5, then the steady state error is calculated as shown in equation 6. Since the steady state error of the system is 0, therefore that compensator is not required. By using LTI viewer, the time response, steady state error, and stability of the system can be assessed without manual calculations. The performance specification from LTI viewer are shown in Table 1, while Table 2 shows the comparison of manual calculation and LTI viewer result. The percentage difference between manual calculation and LTI viewer for the setting time and overshoot percentage are 4.69% and 0.22% respectively, while the steady state error has a percentage difference of 0%.
We will design a compensator so that the system will reach the desired performance, which is the percentage overshoot is less than 5% and the settling time is less than 180 seconds. So with the percentage overshoot and time settling, we can find the damping ratio and also the natural frequency. With the damping ratio and also the natural frequency, we can find the desired location, and then we will find the zero angle and pole angle to find angle deficiency. The result comes out that the angle efficiency is not equal to 2k plus 1 times 180 degrees. Hence, dynamic compensator is needed. By finding the compensator 0 and pole, the lead compensator will be the equation on top, and the transfer function with compensator will be the second equation. Then we will calculate the pole length using Pythagoras theorem, and by using magnetic criterion, K can be found. However, the compensator does not produce a satisfactory overshoot. By using trial and error, the compensating zero is adjusted to obtain S equal to negative 0.0081 and pole is located at S equal to negative 0.04412. The updated transfer function with compensator with K found with same procedure is shown.
I'm Chizing, metric number U2103097. Now I'm presenting about the MATLAB design part. So we have used CISO2 to add a compensator in convection oven control system to achieve a setting time of less than 180 seconds and keep the overshoot below 5%. To achieve the specification, we create a lead compensator and adjust the pole zero position so that the root locus can overlap with the intersection point in the diagram, which indicate that we have met the specification. After the adjustment, the final zero position in S-plane is negative 0.00x, while the final pole is at negative 0.0429. So these are the block diagrams showing the uncompensated, manually designed, and CISO2 design system. From the diagram, we can see that the original system does not have any compensator, while the value of gain and pole zero placement for the compensator of the manual design and CISO2 design is very close. When comparing the two designs, both manual and CISO2 approach successfully met the design specification. The step response for both is almost identical and overlapping on the step response plot, which validate the accuracy of our manual calculation. Both manual and CISO2 design have significantly reduced the overshoot. However, the CISO2 design did achieve a slightly lower percentage of overshoot of 4.66%. And this actually shows that fine-tuning with MATLAB 2 can be easier to provide better results. In conclusion, we have successfully modeled and improved the convection oven control system. Initially, the uncompensated system have a settling time of 917 seconds and overshoot of 14.6%, which are far from the acceptable value. With the lead compensator, we reduced the overshoot to 4.6% and improved the settling time to 180 seconds, meeting all the performance goals. Both the manual design and CISO2 design have achieved the specification. The manual solution proven to be accurate, while the CISO2 have provided a slightly better result, especially in terms of overshoots. The final compensator system is now much faster, more stable, and operate reliably. So that's all from us. Thank you.